Hello everyone, thanks so much for attending. My name is Jan Franke, and welcome to Geolitix 104. This is the fourth in a series of webinars designed to introduce you to the power of cloud computing for geophysical data sets. Today we'll be looking at the concept of basic Gpr processing. Now, Gpr processing has a bit of a reputation of being a bit of an art form, particularly promoted by those who have been at it for years or if not decades. And I think we like to think of ourselves as real experts in the field and we really know a lot about processing. The fact of the matter is there's not much of an art form to processing. There's only a very few sets of algorithms that can be applied to GPR data to enhance them. The real art form exists in the interpretation of the data, and that's where the expertise really comes into play. So, there's only so much you can do, as I said. Much of the processing steps that we use come from seismic data processing, which has been around, well, a lot longer than you or I, and they are well established. So what are the objectives when we process GPR data? Well, there's three sort of routes you can take, right, in terms of objectives. One is, I want to interpret the data as a GPR professional myself. I need to pick my pipes, or I need to pick my rebar, or my graves, or whatever the case may be. It is for my internal use. The next objective may be, well, I want to do that, but I also want to create slices, because slices will help me interpret my data. Perhaps if I'm looking at a pipe data set, right, utilities mapping. Or I want to show those slices to a client, and that's part of my deliverable package, so I want to create the best possible slices I want. Now, those are relatively easy to address. The hardest part, as we all know, is when the client says, well, I want to see the data. Well, that gets much more complicated. Displaying data to clients means that you need to annotate it and you need to be able to describe what's going on, because the client is not a GPR expert. The client's going to ask, well, this looks like a hyperbola, how come that's not a pipe? Or this looks like a hyperbola here, when it's really two arms of a hyperbola crossing, right? So within the text of your report, you then have to go into tremendous detail about managing expectations when the client looks at their own data set. So let's go through each of these issues and how we address that within the Geolitix platform. Now, when we look at GPR processing steps, there's actually really only one processing step that is absolutely necessary to do, when without it you'll get the wrong data, and that's simply declaring where time zero is, right? So where is that first onset of the direct arrival through the air from the transmitter to receiver? Now, most GPR systems record that internally. We do it again within Geolitix, and I'll show you how that works, but that's really really the most important step. Everything else is for your own benefit and for the enabling of the interpretation to take place. So let's go ahead and take a look at a project here, and I'm going to look at this one here. This just so happens to be a figure eight that was done in the Middle East to determine where some GPS lag situations. But the point is that when we bring data into Geolitix, in general, the first thing we see is, well, as I've said before in previous webinars, we see nothing. Well, why is that? Okay, let me explain this in greater detail. Most modern GPR systems are 32-bit now, but it doesn't matter. Just for simplicity, we'll call it a 16-bit GPR system. That means that numbers can be integers, and they usually go from, well, they do go from negative 32767 to positive 32767. That is the value captured at the ADC, so the analog to digital converter, and put into the FPGA in the receiver, and that gets spat out through some sort of port into a recording device. So those are values, and they really come down to millivolts or some sort of voltage level within the antennas, right? And we're recording those voltage fluctuations, and they're very, very, very small. And indeed, they are small. So what ends up happening is, although the manufacturer says we use 16-bit data, 99.999% of the data is clustered around very low amplitude. So say like minus 1,000 to plus 1,000. It doesn't go to 32,000 or positive 32,000. So when you display it on the screen and you tell your grayscale to go minus 32,000 to positive 32,000, but all your data is clustered around the middle at minus 1,000 to positive 1,000, well, you don't see much. You can kind of see some slight banding in there, but you don't see much. So how do we compensate for that? Well, there's two ways of doing that. Some software does what's called a normalization. So what they do is they'll take the highest and lowest values within that profile, and then they'll say, okay, we'll make that white, and we'll make the highest value black, or the other way around, doesn't matter, and that's going to be our profile. And it's an easy way of seeing data very quickly. There's a problem with doing that, though, and that is when you have an array data set or a data set that has perhaps crossed a manhole cover with a lot of metal, right? You get a huge amount of ringing and a lot of amplitude coming back. That one profile will then have a different scaling effect than all the other profiles in the project. So if you go and then make a slice, you'll see some banding, right? So we don't necessarily want to do that. What we recommend is the easiest thing to do is just apply a constant scale, and we in fact calculate that for you. And then just by doing that, we can see, there's our standard, there we expect the air wave and the ground wave to come in. You see our time zero. So to correct for time zero, well, that's pretty straightforward as well. All we're going to do there is well, let's actually explain what a time zero is, right? So you've got a transmitter, you've got a receiver. We'll assume they're on the ground surface. There's two first arrivals that normally occur before any reflections occur, and that is going through the air, which is traveling at the speed of light, which is 0.3 or approximately 0.3 meters per nanosecond, and then a second one immediately thereafter, which is the direct arrival of the ground wave. So that's traveling along the surface of the ground. Now, that ground wave changes in velocity and changes in amplitude depending on what you went through. So for example, if I'm in the middle of a puddle, right, and my transmitter is on one side and the receiver's on the other, the puddle is going to slow down because obviously the dielectric's higher, so it's a slower velocity. That's going to slow things down and probably change the frequency content of my second arrival. So what we usually do is we declare the air arrival as being time zero. That's where everything starts. Everything above that is kind of wasted. And we see some data that clients show us, and it seems that they have a time zero that is halfway down their trace, and that seems to be wasted data, right? You could have, if you can correct that and move it up to the top, that gives you a little bit more of a usable time window. So if we go into processes and time manipulation, and we just simply go time zero correction. Now, that'll automatically find that time zero. This happens to be a data set for the fairly new GSSI antenna, so it's fine. However, if you're using older systems, particularly ones that were made in the 90s and 2000s, some of the transmitter and particularly the receiver electronics were susceptible to temperature drift. So that is, if you were in a cold environment and you started up your transmitter and receiver, your time zero actually changed. It got closer and closer, like it shortened, in other words. And to do that, what we can do is we can go on you can find a peak, but do it on a trace-by-trace basis. Now, in this data set, it really won't make much of a difference at all. But if you do have a variable time zero, you could look at it trace-by-trace, and then we shift everything up as needed. But again, we haven't really seen that with modern radar systems. Those are from the older ones. So that's how time zero works. It's a fairly straightforward application of a simple algorithm to find a threshold value. So let's go on and take another look at another data set here. If I go into my next data set, so I'll go to, here we go. So here's another data set actually from the same site in the Middle East. We're in a courtyard, and again, we see nothing. So we're going to go ahead and add a constant scale just so we can see something. And all we're doing there is just multiplying everything by a certain value, right? So we're just amplifying everything, all constant, down the trace. Everything is the same value. And now we see, okay, so we'll go ahead, we see our time zero. We'll go ahead and declare where our time zero is. We don't need to do a trace-by-trace application. That's great. So that's all we needed to do. Well, you'll say, I don't see anything. And you're absolutely right. You don't see anything. But if you were to interpret something on here, at least it would be at the correct depth. Well, it would be at the correct time. We still need to declare what the velocity is, right? So what's our next step? Well, we gotta gain this up. Okay, well, there's going to be a number of different experiences listening to this webinar. And, obviously there's the GPR guys that have been at it for 30 years, like myself, and there's also newcomers to the field. So let's explain why we need to gain signals up. In GPR, there's a host of loss mechanisms. Into the transmitter, well, the transmitter dumps short impulse of voltage, usually a few hundred volts. Sometimes with high frequency antennas, only 6 volts, right? That's all you really need. the amount of volts that go into the transmitter doesn't have a massive impact on penetration. It's an exponential relationship. So if somebody comes to you and says, I have found a radar system online from Russia that does 10,000 volts, yippee-ki-yay. It's not going to suddenly give you 4 kilometers of penetration. It's not the way the physics works. So anyway, we dump a little bit of voltage into an antenna. That antenna then creates a change in charge. A change in charge from Maxwell's equations creates an electromagnetic field. Now, the amount of voltage that goes in is then, and the energy that goes into the ground is then dissipated by a number of effects. Firstly, we have the antenna coupling to the ground itself. It's not 100% coupling. A lot of energy is lost at the ground surface. And that's particularly true if you raise the antenna off the ground, right? Because then you have that air gap, but that's on a drone application. Once in the ground, you have a whole host of things that make you lose energy. The first one being ohmic losses. So that's actually related to the electrical conductivity of the ground. So the higher the conductivity, so the more clays, the more water with ionic mobility, the less energy gets through, right? It absorbs energy. There's also factors of geometric spreading. A radar is not a laser, it's a flashlight. So the further down you go, the more geometric spreading there is, and there's less energy on your target. And then how much energy actually gets to your target? Well, if it's just a pipe and it's 5 meters down, well, very little energy actually gets to it, and it has to do the whole trip on the way back. But on the way back, as well as on the way down, we have other issues of scattering. So for example, if you're using a 1 gigahertz antenna and you have a bunch of cobble-sized gravel, well, each one of those pieces of gravel is going to be on the order of the wavelength of your antenna, and you're going to have scattering, in which case you're not going to get a lot of energy through. It's the same concept as your headlights in your car in fog, right? It's a scattering effect. So scattering is a loss. There's ohmic losses. There's exponential losses in geometric spreading. And then the other thing is that even if you're using a shielded antenna, not all of your energy is going into the ground. Some of it does escape upwards, and shielding is never 100% efficient. So double all that on the way back up to the receiver, and what you'll find is you may put, let's say, 100 volts into the ground, you only get microvolts or millivolts coming back. So you have a very, very, very faint signal coming back. So to make anything out of this, we need to turn up the volume, basically. And there's a number of ways we can do this. And this is the tricky part, though, right? Which kind of gain you choose to use. Now, a lot of us who have gone through geophysics programs at universities have heard of amplitude gain correction, so Agc gain. And the concept there is to equalize the amplitude by applying a gain which is kind of inversely proportional to the signal strength. But the problem there with Agc is it equalizes everything. So yeah, you see things, but you can no longer determine the relative strength of a reflection. So let's actually do that right now and see what happens. We go to gains, and because gains are so important, look at the number of gains we can apply. There's all sorts of things we can do to it. And if we go to an Agc gain, and we'll just slide the slider up a little bit here, what we'll end up seeing here, it's a fairly large data set, is, well, it didn't gain it enough. Let's continue. Well, let's push this up a bit more. Okay, so now we got a gain on a gain, but so what we see is, yeah, we see lots of interesting things going on here, but really at the end of the day, what are we looking at here? Everything is super gained, and I cannot make out a single reflection of interest. Now, I happen to know there are some pipes under here, and it's very, very hard to see that. So Agc gain is not something that we generally see as being very, very useful. Let's look at some of the other gains. So we can go into, all right, we'll go into here, and we'll say, well, we can look at a manual gain. We can actually just create our own manual gain, and let's say we want to not gain the upper, few nanoseconds. We want to start gaining it down here, so we can go ahead and draw in whatever gain curve we want, and we do see the results fairly instantaneous. Now, in this case, at this site in the Middle East, we happen to know that the ground is surprisingly attenuative. Even though it has a lot of sand present, there's also some clay, as well as potentially some saline groundwater present. So it is an attenuative site, and to compensate for that, we're going to have to increase our gain quite substantially right from the near surface, right? And even then, geez, it doesn't work super well. So we can in fact increase our gain level by using the zoom out button, and we can go almost to an infinite gain to see if we can compensate for that energy loss. And it's okay, yeah, we're starting to see something here, but it's, that's one way of doing things. It's a little bit more complicated. Let's go ahead and take a look at some of the other gain functions that we have available to us. Like a linear gain is very simple. We're just applying a linear gain as a function of time. So we just ramp it up according to time. So the deeper you go, the more gain there is. And there's an exponential gain, same concept, except now it's an exponential function. I'm going to show you what attenuate by horizon is later. The most useful gain that we found is called an energy decay gain. And what it does, it takes the entire profile of the radar energy and it finds the average energy decay, and then it applies an inverse decay to compensate for that. And the nice thing about this type of gain correction is that it maintains relative amplitude. So if you are interested in trying to determine the difference between, for example, a metal pipe and a plastic pipe, this will be important to you. But I'm going to say a caveat there because we've been asked about this quite a bit, and there's some misunderstanding on what GPR is capable of doing. So yeah, GPR can determine the difference between a metal pipe and a plastic pipe with one big caveat, and that is that the depths and the environment are the exact same. So for example, if we have a very strong reflection at the near surface and then perhaps, I don't know, a weaker reflection a meter down, can we say, oh, it's weaker, so it must be plastic? No, we can't. We have no idea what it is because you don't know what the material is in between, and it could just be very attenuative material that decreased the power of that reflection. So it could be a metal pipe, it could be a solid metal bar, and it's so attenuative that the signal looks very weak, right? So yeah, GPR can find the difference between plastic and metal, but in certain circumstances where everything else is equal. So we look at this data set and go, okay, so now we know how to gain this. We usually use an energy decay. What's the next thing we see? Wow, well, we see a lot of these horizontal stripes. What do we do about that? Well, that's pretty common with almost any GPR system. What is it? Well, the horizontal striping is an effect of primarily internal receiver noise. So the receiver is so sensitive that any other sort of oscillators or anything going on in the receiver creates its own electromagnetic interference. That often is a cause of these horizontal bands. Another cause is using shielded antennas. Now, the concept of shield is just a Faraday cage around the antennas, but if you put too much power into that transmitter, yes, some of the energy goes down, but some of the energy also goes ding, 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 and bounces around within the shield. So shielded antennas particularly can have an effect, particularly if they're not perfectly tuned and they don't have radar absorbent foam on top of them. You could have a ringing effect. So we need to get rid of that. And there's a few different ways to doing that, but the simple way of doing it is what's called a background subtraction. So what does that mean? All we're doing is we're calculating the average traces, so the average amplitude of traces over a window of traces. So let's say we use, okay, over 100 traces, what's the average trace? And we subtract that on a moving average, right? And we can do that for the whole profile, or we can do it for just a trace window. So in this case, look what happened here. So let's zoom in a bit. We've used, 99 traces. And that's great. We can see some interesting hyperbolic features here, and here, but we've also lost a lot of that geological information, which might be of interest. So one way to get rid of that, to keep that geological information, is to increase our background subtraction trace window, and that starts bringing back some of that important information that might be of interest in the upper area. But there's a risk in doing that, and this is a great example. So I'm going to assume here that they went over some sort of metal object. It might be a manhole cover or something, but look what's happened here. There's a blurring effect because as you use that moving time window past a very strong amplitude event, there'll be a blurring effect, and there's not much you can do about that with background subtraction. There is another method that we can use to deal with this background subtraction, and that is in a 2D FFT way. I will show you how that works, but it is it's very effective, but it's also you have to be very careful in how you use it. I'm just going to take that energy decay and actually smooth it out. So there's a little bit more smoothing, and we might be able to get a bit more smooth curve here, because you can see here a little bit of grayscaling going on where, well, it didn't, yeah. So it makes the grayscale a little bit smoother if you move the smoothing window of the energy decay upwards. So now we've got our background subtraction done. And, you know, from this point on, we're basically done. We can now go ahead and find a hyperbola and interpret this data set as much as we want. That's about it. So there's no, you know, secret sauce involved here. You know, we can go into much more detail, which we will in a second, but that's basically what you need to detect pipes, right? Anything else is kind of icing on the cake. So it's not icing on the cake, it's superfluous, because you know, we get asked, for example, bandpass filtering. The concept of bandpass filtering, yep, we can do that. We'll just go ahead and bandpass filter. Now in this data set, let's say we wanted, I think it was a 350 megahertz system. We can say, yeah, I want to go from, I don't know, 130 and have my maximum at, you know, well, let's call it 500 megahertz. Does that really make a difference? Because remember, if there's stuff that's going on outside of the wavelength of that, or the detection range of that antenna, you can't pick it up anyway. I mean, that's not how antennas work, right? So the only reason you would do this is if you have a specific frequency of noise that's going on. For example, if you used an RTK GPS radio that happened to be at 415 megahertz, which would be really stupid to do for utilities detection work, then you'd get a lot of ringing at that frequency, and you could possibly do what's called a band stop or band notch filter to remove that. It's not going to work right now because I'm about to notch out all the important data in my profile, so I don't see anything there. So bandpass filters, I've in 30 years of doing this, I've not really seen for utilities detection a tremendous use for them. There are some uses in geological mapping, which we'll get to in a little bit. So let's go on to another project and go to the next phase of processing, which is not just for your benefit of picking individual targets, but maybe now you want to create a slice project, right? So we'll go into processing for slicing, and then we'll go ahead and take any data set here. It doesn't really matter. So again, we'll do this constant scale, and this is some GSSI data, but it doesn't really matter. Let's go ahead and do a time correction. So that's fine. And we'll do our standard energy decay, and I will slide that up a little bit to smooth out the samples. Okay, and we can see we have that ringing. That ringing is always going to be there, and in most GPR data sets from most manufacturers. We can take that out. That's actually the default's pretty good there. We'll leave that as that, and we can see some nice hyperbolas there. So now, if I wanted to ignore the slicing thing and just go ahead and interpret this data, yeah, I can pick that one, I can pick that one, I can pick that one, and I can go through this all and line by line, I can go through it and determine where each of my hyperbola are. That's fine, but we want to be fancy and we want to do some slicing. So what's our first step in slicing? Well, first step is to actually migrate it. But before we migrate it, we really need to know our velocity. So in Geolitix, we go to Interpretation, and we take our Estimate Velocity tool, and we place it on an obvious hyperbola, and as you can see, I've already done this, and it comes out to about 0.081. I'm working in meters per nanosecond, so that's fine. It's a bit of a damp ground environment, and we can see our pipes quite clearly here. So how do we do what is migration? Actually, let's start off with that. Migration is an attempt to mathematically take the energy of that hyperbola, so both the apex as well as the asymptotes of the hyperbola, and mathematically collapse that down into a single point. Now, this has been done in seismic for, probably a century. In GPR, there are a number of ways of doing it. We implement one fairly consistent and a way that works. There are other ways of doing it, and we're actually bringing on some in the coming months. But let's go ahead and do our migration routine. So it's under filter, and you say migration. Now, the algorithm needs to know how far out should I look for this energy to collapse downwards. Well, I can say, I don't know how many traces. Usually I find about 25 traces, but So let's see what happens. This is the original data up here, and this is our migrated data set. What I'm trying to do is for each one of these hyperbolas, and you can see some of them are stacked on top of each other, so a little hard to make out. I want to make that as clear and crisp white, black, white, in this case, polarity point as I can, right? So I'm going to take it a little bit more, maybe. I mean, this is a nice, oh, there you go. So that collapsed it fairly nicely at that level. And this is the nice part about having cloud processing. It is simply a slider, right? So I can slide it back and forth and see the immediate results. So now I've got my data collapsed into the hyperbolas that I want, or the hyperbolas collapsed into these points that I want. But if I go ahead and grid that, that's not going to work very well because I have negative values and I have positive values. What I now need to do is apply what's called a Hilbert transform. What's a Hilbert transform? Well, it takes that wavelet, which is a negative, positive, negative in this case, and tries to fit what's called an envelope around it. So literally it's an envelope function, it's also called. And in Geolitix, it's very simple. You just go to Filters, Hilbert transform, done. Okay, so now my little sequence of, my sequence of white, black, white became just a dark spot. And in fact, every one of my pipes became a little dark spot. This one became a dark spot. And that's how I start my gridding, right? So from there, I just grid out dark spots. And my job then is to trace out where the dark spots are. So that's how we do gridding. And really, I've just described all of Gpr processing in a few minutes. Fairly straightforward stuff. Yes, Geolitix has lots of other features. I'm going to go through them now, but much of that is not super relevant to finding individual targets, for example, right? So if you're looking for discrete targets. Let's now look at something a little bit more complicated, and that is a geological project. So let's go to, I called it part 1. So this happens to be an open pit mine, and they're doing some blasting. And let's go ahead and look at these profiles. This is sensitive software data. It doesn't really matter what it is. But again, so here we are. We can see where we are in the open pit mine. We'll pick one of, we'll just randomly pick this one. Can't see anything. We apply our constant scale as before. And we start saying, oh, okay, this is kind of neat. We actually see some interesting stuff there. Now in this case, the amplitude that's come back is so good because this is a gravel pit for the most part, or it's a sand and gravel pit, that you're getting a lot of information back right in the near time here. In the 100 to 200 nanosecond range. So we're getting a lot of penetration with this. But of interest to us is this near surface layer. Do you see that up here? We want to try and map that out. So what's the easiest way to do that? Well, the first thing is let's just zoom in on that. It does not need to be, we don't need to look down 300 nanoseconds. We are only interested in that first 100 nanoseconds. Well, let's go ahead and perhaps increase our vertical scale here so we can see things a bit more. You can do that in Geolitix. And then go back to our processing and say, look, I only want to look at the first, 150 nanoseconds. So I'm going to remove everything below, 130. So now I'm really focusing on this upper zone. Let's go ahead then and add our energy decay, which should work pretty well here. Yep, we start seeing it now. This is great. All right, so I can kind of see where I want to go, and I can kind of see this near surface layer. But, there's this airwave reflection that kind of gets in the way. Maybe I should do a background subtraction. Well, let's see what happens if I do that. Now, instead of taking the default, I'm going to slide it down to a very short number. Holy crap, what happened? It all disappeared. That's right. So, background subtraction is also a bit of a dangerous thing because if you use too short a trace window, too short of an area to average over, all it will do is highlight steeply dipping interfaces and completely eliminate anything flat. So look what it did. Here's a bit of that horizon. We can see it quite clearly here and draw it in if we wanted to. All that's left behind with background subtraction, if I use too short a trace window, is just that ramp there, right? So let's go ahead and do too long a time window or a trace window, and really not much has happened. It has improved things a little bit, so we want to find something in the middle. And personally, I find around 100 traces, depending on your step size, of course, seems to be enough to get rid of most of the flat-lying instrument noise, right? So now we can see this thing. It seems pretty straightforward. I like it. What's the next step? What else can we do? Well, I'm going to show you DWOW in a second, but let's say, okay, let's go ahead and actually attenuate by horizon. So let's say we were showing this to a client, and the client's going to go, oh, what's all this? There must be some geology there. Well, there is actually. But in this case, maybe we want to hide that, or maybe we want to just subdue it down. So we can go ahead and add an interpretation. We'll say base of, I don't know if it was sand, whatever, and it's a horizon. And let's go ahead and sketch that in. In fact, some of this might be, it's so clear we might be able to do it automatically and have the computer trace it out for us. But in our case, we'll just draw it out. And you can move left and right with the arrow key on your keyboard or on the screen or by dragging your mouse in a pan function, but I'm not doing a very close job here, but you get the idea. All right, we can then go back to processing and say, you know what, I want to attenuate by horizon. I want to pick the base of sands, and I want to attenuate everything below it at a certain level, 10 dBs, there it is, and oh, I don't want that sudden effect there. I can fade it in over a few nanoseconds. So that's one way of drawing the viewer's eye potentially to an area of the profile that you want them to look at. It is bordering on photo editing there, so you do want to be careful about how you use it. What we use it for is for bathymetry surveys, where sometimes the water column just has some weird effects that you don't want necessarily a client to start questioning what that all means, and you have to explain even the temperature effects on the transmitter and stuff like that. So we tend to attenuate things above the bathymetry, so in the water column. That would be one way of doing it. So let's look at another thing we can do on this data set, because it does have some very interesting features on it. Let's do a Sobol transform. A Sobol transform is a kind of a neat one because it's based off the image processing space, where it's an edge detecting algorithm. So I'm going to show you what that does. Now you might go, holy crap, what's going on here? Well, it allows you to trace out individual targets with a little bit more clarity than just looking at the standard grayscale display. But what's also interesting, and I'm trying to see if there is, okay, so it also enhances bedding features sometimes. So can you see, now let's assume this is a sand pit, which I think it is, and there's sand atop, you know, something else, call it gravel. It doesn't really matter, and we can't really tell what it is. But the point is, can you see that there is a general banding going on, or a bedding sort of feature that goes on in this direction? That wasn't super obvious in the original profile, but with the Sobol transform, you actually can see and almost be able to sketch some of those out if you were interested in the exact bedding geometry of that sand layering. So that's really interesting stuff if you're doing complex aeolian studies or alluvial studies with GPR. Now, I'm going to go to one last case study here, and this is, I particularly and purposely picked a bit of data that didn't have GPS, because guess what? GPS almost wasn't invented at the time. This is stuff I collected in South America, in Guyana, actually, for an alluvial diamond project about 25 years ago, with some very, very old sense and software systems. But I chose it because it's just absolutely gorgeous data, but it also shows another interesting effect that happens with GPR, and that is what's called the wow effect. So the wow effect is caused by two things. It's either an inductive, a coupling and inductive effect of the antennas to the ground itself, which manifests itself as a very, very low frequency content, a bit of information that's, you might be able to pull something interesting out of it, because I suppose there's some capacitive resistivity, capacitively coupled resistivity information that could be buried in there. It's never been done. Yes, there are Ukrainian and Russian systems that claim that they can produce, you know, hundreds of meters of penetration based on the wow information. No, that's not how it works. I mean, in this case, we knew we went over puddles, and that's created the wow. And the other thing is the old dynamic range limitations of the older radar systems. But the point is, the wow manifests itself as these vertical stripes. So let's go ahead and gain this up with an energy decay. And we should really see this wow effect. Now, somebody might go, oh, wow, what is this? It's really of no relevance, but we want to get rid of it. So we will go ahead and add our time zero correction. Okay, so now we have everything in the right space in time or in depth. And we want to get rid of this wow effect, so we go to our filter, dewow, and we select a window where we can still see the reflections quite nicely, but we lose that vertical striping effect, right? So we can even do a larger window than that. So that's how a wow effect works, or a dewow works, and it basically is a low cut or a high pass filter. That's all it is. There's really nothing fancy about that. This data set actually gives us an opportunity to show you a couple other interesting things when it comes to trace editing. So this was done with a very, very, very old radar system which was super sensitive to vibrations and noise and even dirt in the fiber optics. So what we can see here is there's a couple traces that we had a little bit of dodgy data, and that's probably because it was the jungle, it was the mid-90s, and we were using electrostatic plotters basically. So I want to maybe delete some of these bad traces just because they don't look very good or they might impact my later processing. So I can go to trace manipulation, for example, remove traces, and I can zoom right in and say, I want to kill that one. I just click on it, and there it goes. So, and then I can remove this entire section of bad data, or perhaps we went over a log or something. So I can go ahead and kill those, and then as soon as I go to the next data set or the next processing step, they're all gone, right? So that's one way of eliminating data, but there's a whole bunch of really other interesting trace manipulation things we should just quickly go over. So mute traces, that's the same thing as removing it, except it turns everything to 0. So they still stay in their right place. In a GPS coordinate, it'll still have a GPS coordinate, it just won't have any amplitude. It'll be a blank trace. And the final one to look at is idle traces. That's good when you're doing a GPS survey over rough terrain. What you'll find is quite often, if you stand in one place long enough, the GPS wanders about, and that adds distance to the profile. So yes, you can edit that out in positioning, but this also allows you to eliminate traces that are exactly the same to within a user set threshold. So that brings all that data back together. And the other really important step here is resampling traces equidistantly. So what that is a rubber sheeting function which you use with GPS surveys, right? So when you're dragging with a cart or pulling with a vehicle or you're just using a GPS, you may have an odometer, but you're relying on the GPS for positioning, and you're essentially relying on the GPS for the step size. And what this does is allow you to resample the data in the spatial domain to whatever step size you want. So for example, if I was driving or towing a Raptor array system down a road, I'm driving at 30 kilometers an hour. Oh, but there's a school bus in front of me. Now I got to slow down to 10 kilometers an hour. What's going to happen is that, yes, there'll be an odometer, but if I look at my traces, they'll all be squished together or they'll be spread apart depending on how fast I went. And spatial resampling allows us to rubber sheet everything back into whatever step size I want, be it 10 centimeters or 50 centimeters or 2 meters in the case of a low frequency antenna. So those are the basic functions that I want to go over today. We want to keep these webinars pretty short, so that's essentially what I wanted to talk to you about today. Our next webinar will be coming up, so stay tuned. If there are any questions, we'll have our usual question and answer period coming up shortly. So thank you very much. All right, everyone. So how are we doing on our chats here? I haven't looked over that screen. Oh, good old Adam Cook from the UK. Hi, Adam. So he's asking about applying an energy decay gain to an entire data set. And yep, we recognize that there are use case scenarios that need that, and we will implement that as soon as possible. Hopefully in the next week or so, we'll have that available. It's been a bit of a long webinar. If there are any other questions, you know how to contact us on LinkedIn or through our support channels, and we will hold another webinar after the new year. In the meantime, if there's any subject matter that you guys are interested in hearing about as something specific to GPR processing or how GPR works in general, happy to do that as well. Write to us and we'll happy to consider that and do a webinar specifically on that. But guys, thank you very much for attending, and we'll see you next time.